Hello everyone, Mr. Schultz here, and we're talking about Integrated 1, Chapter 3, Section 5, the shapes of graphs. So the first thing we're going to talk about is line symmetry. With line symmetry, we pretty much can fold over a graph, and it will look the same if we flip it. So sometimes you can have the line of symmetry over the y-axis. Sometimes it will be over the x-axis. So for example, if we had a non-function that looked like this, the line symmetry would probably be over the x-axis. Now this is a poorly drawn. Don't worry about it. Now sometimes it's not going to be on either of the axes. It's going to be, where y equals, or x equals, -1 right here. That's this one right here. It's still symmetrical. It just doesn't have to be on the x-axis or the y-axis. So determine whether each function has line symmetry. And explain. Okay. So let's look at these right here. Okay, looking at these, I'm going to type up some things. So for the first one right here, there is no line that can be drawn to make the right half mirror image of the left half. So this has no line symmetry. And going back to the top one right here, this would not be a function because these inputs would have more than one output. But this is an example of showing a graph with line symmetry. All right, well, looking at this, the second one right here, we can tell that, hey, look, let's make it red. It looks like if we fold it along this line right here, then it would be symmetrical. The left side would be symmetrical with the right side. So the function g of x has line symmetry over the equation y equals, x equals 1.5. Yeah, that's where we drew that red line right there. So let's go on to the next one, h of x. Well, h of x is a parabola, like x squared, except we're not going to go into what the exact function's equation is, but we're going to say the function h of x has line symmetry. The line symmetry is over x equals -2. Now, if we were to draw it, we would see that, hey, right, there we go. It would be right here. The left side mirrors the right side. All right, last one. Now, if I try to be like, all right, this is the exact middle right here, and it flips over, well, no, because if I flip this over, it would kind of look like this. Like it comes down, and then comes up, and then comes down like that. So if I flipped it, it wouldn't reflect upon itself. So this, the function k of x does not have line symmetry. All right, let's go on. So interpret symmetry. Fountains. A fountain is spraying a stream of water into the air. The solid portion of the graph represents the path of the water, where x is the distance in feet from the fountain and y is the height in feet of the stream. Find and interpret any symmetry in the graph. Okay, so it looks like this is one of those parabolic shapes, also known as a quadratic. So it looks like we have line symmetry over x equals 2. All right, so let's write it. Well, I'm going to do black. there is a line symmetry over x equals 2. So the height, it goes up, and then it doesn't have enough power to keep going up, so it comes down. So the water goes up, and then when it does not have the power to continue, that's the point, starts coming back down. Or like when you throw a ball up, it'll go up and then come down. If it goes up at a speed, then it'll come down at the speed. That's about it. Alright, let's go on. So now we're going to learn about the extrema of graphs and the functions. So we're going to learn like when it's increasing, when it's going up, when it's decreasing, when the graph is going down, also the relative minimum and maximum. So we're looking at this graph right here. We can determine where it's increasing and where it's decreasing, determining with the parts of the graph. Alright, so looking at this, this graph has certain parts right here. So let's switch to this part right here. Let's say at this point, it starts going up, depending on which way you're looking at it. So if we're gonna say, hey, we're gonna read. So reading this graph from left to right, when x is greater than 0, the graph is going up. So it is increasing. Now, if we're reading from left to right, the graph is decreasing when x is less than 0. If we read from left to right. But if we're talking about our point, if we're talking from our point and like we're relatively from x is 0, it's increasing as we go away from x is 0. It just depends on how are you describing it. Because there's multiple ways for you to describe it when you describe a graph. Alright, let's go on. So, example 4. It says, determine extrema of the graph of a function. Determine the extrema of f of x, then identify each point as a relative maximum or relative minimum. Alright, so let's jump into this. Looking at this, we can determine that, the extrema of the graph. The extrema of the graph of function f of x are b and c. B is the highest point in comparison to everything else. So if we look at B right here, it's like, hey look, B right here, it's like at the top. So B would be considered the relative maximum since it is the highest point in comparison to points around it, relative to the points around it. Point C would be considered the relative minimum since it is the lowest point in comparison or relative to the points around it. Now we're practically just talking about the y values of it. Now we're not talking about the x values, we're talking about the y values or the output. Because when we're talking about functions, we're talking about inputs and outputs. And outputs are what we look at the most. We don't really care about the inputs, except for the fact that every input has exactly one output. Alright, let's go on. So, interpret extrema of graph of the graph of the function. All right, let's go on. So it says a comic book store uses a function to model its profit in thousands of dollars given the price in dollars that it charges for individual issues. Determine whether point D is a relative minimum, relative maximum, or neither. Then interpret its meanings in the context of the situation. All right, let's go on. Let's talk about it. Well, looking at it, point D is relative to all the other points. It's the highest or the maximum. So point D would be the relative maximum since its y value is the highest relative to other points. Now, going further into it, we would further say, hey, point D represents the highest profits that the business could make. So looking at it, like, hey, look, at D, they make about like $80,000. If you go any point away from D, they're making less money. All right, let's continue. Forget about this example 3. I think that's from the previous one. Let's go on. End behavior. So end behavior describes the values of functions, at the positive and negative extremes in the domain or the input, the x values, as we go all the way to the left or all the way to the right, or depending on which way I'm facing, it doesn't matter. It's the end behavior. So as we move left, looking at this, as x decreases, the y is increasing. For this one, as we move right, as x increases, y decreases. I actually love this one because you look at it and you're like, what's happening? Okay, it's going up. As x decreases, like go left, is it going up or down? As x increases, is it going up or down? That's it. Let's go on to example 6. Determine the end behavior of the graph of linear function. So determine the end behavior of f of x. Okay, well, as we decrease the x value, as we go left with the x, the y value is going to decrease. As we increase the x value, the y value increases. Let's type it up. As the x values decrease, the y values also decrease. As the x values increase, the y values also increase. The only thing I would probably say to make this, if we wanted to jump further into this, is to say, do they increase at the same rate? But we don't need to jump into that. That's just an idea. All right, let's go on. Example 7. Determine the end behavior of the graph of a nonlinear function. Okay. Well, basically, what we have to do is we figure out, all right, at a certain point, we understand that it's always going to go a certain way. So look, as we're going this way or we're going that way, at a certain point, we have certain things that are happening. Like we figure out what are the zeros of the graphs. The zeros are like the x and y intercepts. And then we figure out, all right, at what point is the end behavior starting? So looking at this, hey, look, there's origin right here. It doesn't touch anything else, but it's going to be going down. At this point right here, we have the other x-intercept right here. That's the x and y-intercept right there. At this x-intercept, it's going to go increase. So just looking at it, I can make that determination right here and say, hey, this non-linear function end behavior is the following. At 0, 0, from 0, 0, as x decreases, the y value decreases as well. I would also say it decreases faster than the x value is decreasing. From x, from I would say 6, 0, or the other x-intercept, I would say as the x value, remember it's the x value, not just x value increases, the y value increases as well. So once again, when we look at this, technically, I would say the end behavior. Oh, go back there. There we go. The end behavior right here would start right here and right here, going as we decrease or increase. Our x values decreases and our s value increases right there. Bye, guys. Thank you very much, and I will see you in class. Bye.